Example: integrate x squared minus x plus 1 over x plus 1 raised to the power of 3. First, we decompose into partial fractions, getting a over x plus 1 plus b, x plus 1 raised to the power of 2, and c, x plus 1 raised to the power of 3. As you notice, the last term, c over x plus 1 raised to 3, is the highest exponent of the main functions. After getting a common denominator, adding fraction and creating numerators follows that a times x plus 1 is power 2 and b x plus 1 times c equals to x squared minus x plus 1. Then we substitute the value of x, and mostly we do was find the root of the functions, but can only apply in the first repeated term, and mostly it also apply in this distinct. But this time we're going to find or assume a number that can make the other zeros, the terms to other zeros, and the targeted coefficient will not become a zero. Here we let x equals to negative 1, then we come up c equals to 3, then x equals 0, then we come up a function a plus b equals to negative 2, but we're gonna leave it in that way. The important thing was that it doesn't become 0. Then that x equals to 1, then you come out of another function, 2a plus b equals to negative 1. It follows that b equals to negative 3 and a equals to 1. Then we're going to integrate it by assigning the values of a, b, and c into the partial fraction. As we can see, the terms of the partial fraction can now be integrated using integration of logarithms and the general power formula. By applying the necessary integrations, we arrive to this function. Now we have the solution to the integral, which is ln x plus 1 plus 3 over x plus 1 minus 3 over 2 times quantity x plus 1 squared plus c. For our second example, we shall integrate this following integral: x cubed plus 4 over quantity x squared minus 1 times quantity x squared plus 3x plus 2 dx. Again, we will decompose the integral into partial fractions by factoring the denominator with its linear factors. Now, we will arrange the partial fractions to this form to solve for the numerators. Now, by algebraic manipulation, we now get to this equation. Now, we will substitute values for x
in which the other terms will be zeroed out. In this example, let's substitute x to -1, which in turn zeroes out the first, the third, and the fourth term, thus giving us the value for b, which is -3/2. Let's substitute x to 1, so we get c equals 5/12. Substituting x to -2 will give us the value of d, which is 4/3. We will use the values of b, c, and d to find for the value of a. Now, letting x equals to 0 and having the values of b, c, and d, we can now solve for a, which will become -3/4. Now that we have the values for our numerator, we can now proceed with the integration. We have used the integration of logarithms and the general power formula to arrive at this function. By simplifying this, we have the answer as -3/4 ln x plus 1 plus 3/2 over x plus 1 plus 5/12 ln x minus 1 plus 4/3 ln x plus 2 plus c. Now, we will evaluate the following integral: x cubed plus 2x minus 1 over x cubed minus x minus 2 squared dx. We shall factor and decompose it into partial fractions. As we can see, there are two repeated linear factors. We factor the trinomial in the denominator into its binomial factors. Now we will set up the partial fraction into this form and solve for the numerators. By algebraic manipulations, we transform those fractions into this equation. Again, we shall assign values to x in which we'll zero out the rest of the terms and get the values for our numerators. Next, we will assign those values into the numerator of our partial fraction. Next, we will integrate the resulting function to get the following answer: 7/27 ln x plus 1 plus 4/9 times x plus 1 plus 20/27 ln x minus 2 minus 11/9 times x minus 2 plus c. What we did earlier was partial fraction decomposition, which is a technique used to write a rational function as the sum of simpler rational expressions. In this section, we will discuss about partial fractions that has irreducible quadratic factors. It is so when the denominator has a factor which is quadratic with rational or complex roots. There is a different technique for solving these types of partial fractions. For example, this rational function x squared plus 8 over x cubed plus 8, its denominator can be factored as the sum of cubes. The quadratic factor has complex roots, so it cannot be factored any further. The term on the partial fraction with a quadratic denominator, instead of having a constant numerator, it will have a linear binomial numerator, as seen in the example. In this example, the quadratic factor is x squared plus 1, and its numerator will be represented by bx plus c. Now, we will use algebra to get rid of the denominators. We shall expand the parentheses and group like terms. Now, at this point, we will have to compare the terms on the left side and on the right side of the equation. First, we will compare the constants, wherein we will have the value of a which is equals to 1. Then comparing coefficients of x, which give us the value of c which is equals to 0. Then we compare the coefficients of x squared, which give us the value of a plus b which is equals to 0. We already know that a equals to 1, so b must be equal to negative 1. Now that we have the values for our numerators, we will get back to our integral and assign those values to integrate our decomposed partial fraction. Applying the necessary integrations and simplifying our answer, we get ln x over square root of x squared plus 1. Compute the area of the region enclosed by the graphs of the equations y equals to cosine x, y equals to sine x, and x equals to 0. Begin by finding the points of intersection of the two graphs. From y equals to cosine x and y equals sine x, we get that cosine x equals to sine x. Therefore, sine over cosine x equals 1. That is, tan x equals to 1. Which in turn give us the value of x, which is pi over 4. Now, we shall look at the graph of the enclosed region. Now we can see the area bounded by the graph of y equals to sine x, y equals to cosine x, and the y-axis. So the area of this region is given by the integral from 0 to pi over 4 of cosine x minus sine x dx. And so by integrating and subtracting the lower limit from the upper limit, we get the area of the bounded region, which is square root of 2 minus 1. Compute the area of the region enclosed by the graphs of the equation y equals to 8 over x, y equals to 2x, and y equals 2. Begin by finding the points of intersection of the three graphs. From y equals to 8 over x and y equals to x, we get that 8 over x equals 2x. Therefore, 8 equals 2x squared. Then, 4 equals x squared, wherein x equals 2. From y equals 8 over x and y equals 2, we get that 8 over x equals 2, wherein x equals 4. From y equals 2x and y equals 2, we get that 2x equals 2. Therefore, x equals 1. Now, see the given graph of the enclosed region. Using vertical cross-sections to describe this region, so the area of the region is equals to the integral from 1 to 2 of top minus bottom dy plus integral of 2 to 4 top minus bottom dy. Filling in the values and doing the necessary integrations, we get that the answer is 8 ln 2 minus 3.